Hi there. Today we're going to go over types of waves. This is Heat 3 of Unit 8. Our key ideas: what carries a wave, how are waves generated, and what is the difference between a transverse wave and a longitudinal wave, and how do the particles in ocean waves move. So let's start looking at what is a wave, or what carries a wave. A wave is a disturbance that carries energy through matter or space. So it can be transferred through an object or just the air in general. So we've got waves that we see all the time, and we'll look at specific examples here in a minute. But common time we see waves is like on the water. So if we look at this visual here, we've got the wave motion that's going from left to right. But if we see a leaf sitting on the wave, the leaf just kind of sits motionless. It'll sit in this one spot, even though the wave motion is going from left to right. So it'll stay put. So most of the time waves are going to travel through a medium, and a medium is just an object, whether it's a fluid like water or an actual solid object. Typically we don't categorize air under this, so we don't. Oh, here we go. Physical environment, which phenomena occur. So we've got water and things. Mechanical wave is a wave that requires a medium through which to travel. So these waves definitely do require a medium. So water, for example, sound waves, so those would be mechanical waves. Whereas an example that where a medium is not needed would be light. Light acts in a wave pattern as well, but it does not require a medium, so light does not fall under this mechanical wave category. We'll get to that a little bit later. Electromagnetic waves, like light, is a wave that consists of oscillating electric and magnetic fields which radiate outward at the speed of light. So traveling at the speed of light. Visible light waves, radio waves, X-rays, ultraviolet rays. What does the electromagnetic spectrum consist of? The electromagnetic spectrum consists of light at all possible energies, frequencies, and wavelengths, and we'll talk about these terms here a little bit. The visible spectrum is only a small part of the electromagnetic spectrum, and each part of this electromagnetic spectrum has unique properties. So we'll see a visual here. So we've got the electromagnetic spectrum. It's arranged from a longer frequencies, or longer short wavelengths, which is a very low frequency, to a higher frequency. So it goes from left to right. Typically we measure wavelengths in nanometers, but we've got some centimeter lengths here as well. And then hertz is just how many, say, waves we have each second. So waves per second, or oscillations per second. Alright, so what I want to do is draw our attention here. Visible light is where we see light at. Contains all the colors that we can see. And then we can go to lower wavelength. Longer, so we can see that infrared is below red. We've got microwaves that fall under this, radio waves, so those would be below the red side of the visible spectrum, or the infrared side. So these are the longer wavelengths. If we look at the other side, or ultraviolet, or beyond violet, above the violet, we've got X-rays, gamma rays. These are the rays that we have to watch out for when we're out in the sun, so these are the ones that can actually cause skin damage. Alright, radio waves we know are used in communications as well as radar. These have wavelengths that range from tenths of a meter to thousandths of a meter. Radar is just a radio detection and ranging system that uses reflected radio waves to determine the velocity and location of objects. Interestingly, there are mammals that use radar, like dolphins and bats. Microwaves are used in cooking and communication as well. and these have wavelengths that are in centimeters of length. We can feel infrared light as warmth, and actually if we were to have an infrared camera, we would actually glow a little bit because we do give off heat, and we don't give it in the visible spectrum, so we don't glow. But if we had a camera that could detect this heat, then we would appear to be glowing under that camera because we give off this infrared light. Infrared is slightly longer wavelength than visible red light, so the wavelength gets longer. Frequency actually decreases. Sunlight contains ultraviolet light. The invisible light that lies just beyond the violet light falls into the UV portion of the spectrum. X-rays and gamma rays we use in medicine. We're doing X-rays, obviously. So, X-rays have wavelengths less than 10 to the 8th meters. Gamma rays are electromagnetic waves with very high energy. These are ones that can cause damage to our skin. They're very penetrable. So, what is a wave? So, we can talk about wave transfer energy. Tsunamis carry enough energy to cause damage to coastal towns, so this is an application or an example. The energy of normal ocean waves breaks up rocks into pieces to form sandy beaches, so these are transferring that energy that causes something to happen. We could spread out as the wave travels, so the energy is going to continue to be transferred. When sound waves travel in air, the waves spread out in spheres, so it looks like little circles. Maybe we've got a radio tower, well, it's going to be radiated out in all directions. So as these waves travel outward, the spheres get bigger, so the energy spreads over a larger volume. So we start out really small, and then we get larger. And then we've got vibrations and waves, so how do we generate waves? Most of these are caused by vibrating objects. So the sound waves produced by a singer are caused by vibrating vocal cords, whereas electromagnetic waves may be caused by vibrating charged particles. So we can apply a charge and excite those particles and then cause light to be produced. For mechanical waves, particles in medium through which wave passes vibrate too. So we're passing the wave through water. The water particles are going to vibrate as well. The mechanical energy of vibrating mass spring will change forms. So here we've got a mass hanging on a spring at rest. If we pull it down, we're adding elastic potential energy, and as we let go, the mass has kinetic energy. And then when it's above this stable line, we've got kind of a combination of elastic and potential, and then it's coming back down with kinetic, and then it keeps oscillating like this. And then we call this simple harmonic motion because it's in a harmonic pattern. A wave can pass through a series of vibrating objects. So the disturbance travels down the row as energy is transferred from one mass to an object. I guess this could be similar to Newton's cradle, where we hit one object into the other and we get this kind of wave pattern. Here we've got a series of masses connected to springs and then connected to each other as well. So if we do work on one, then they're all going to move like waves through these masses. Alright, we've got transverse and longitudinal waves. The difference between transverse and longitudinal. Transverse wave is a wave in which the motion is perpendicular to the particle motion. So let's say we've got a particle going across the page from left to right. Transverse will basically make what we call a sine wave. It'll oscillate around the direction that it's going. Whereas a longitudinal wave, in which the wave motion is parallel to the particle, so the particle's moving left to right again, but then the wave is kind of, if we had a slinky, it would go in and out, in and out, in and out. Alright, so we say transverse waves have perpendicular motion. So we can define transverse wave, a wave in which particles of medium move perpendicular to the direction of the wave is traveling. Longitudinal waves have parallel motion. So we can define longitudinal wave in which particles of the medium vibrate parallel to the direction of the wave motion. We can talk about the properties of waves. So waves have crests and troughs, or we can call these compressions and rarefactions. So here we've got an example of transverse waves where we've got crests would be the top of the wave, a trough is the bottom. Well, we don't have these crests and troughs in a longitudinal wave. So where the springs, for example, or the waves come together, they're compressing. So we call it compression. And then where they're spread out, this is called rarefaction. Crest is just the highest point, trough is the lowest point. Compression is crowded areas of longitudinal waves, and the rarefaction is where the stretched out waves are at. Alright, so surface waves, how the particles in ocean waves move. Particles in a surface wave move both perpendicular and parallel to the direction in which the waves travel. Define surface waves, waves that occur at the boundary between two different mediums, such as air and water, so we can see the waves go up and down on the water. And that's all I've got. Thanks for listening.